global cataclysm, the Younger Dryas really ticks all the boxes as a worldwide disaster, which definitely involved sea level rise, both at the beginning of the Younger Dryas.
12,800 years ago, something interrupted history. Not gradually, not over centuries, almost overnight. The climate reversed. Glaciers advanced. The largest animals on Earth disappeared. A culture that had spread across a continent vanished from the archaeological record. For 1,200 years, the planet slipped back toward ice. The official explanation is water, but in the exact layer where the cooling begins, there are materials that should not be there. And now AI has read that layer across 4 continents at once. And what it is finding is making the official explanation very hard to defend. Subscribe if this is the kind of history you want more of, because this one goes all the way to the bottom. The world before the disaster. To feel the full weight of what the Younger Dryas was, you have to first understand what it interrupted, because the world it destroyed was not primitive. It was not barren. It was not a world of people barely scraping by in the cold. It was a world on the edge of something, a world in the middle of becoming, and the Younger Dryas stopped it cold. 14,000 years ago, the Earth was warming. The last great ice age, which had kept the northern hemisphere locked under ice sheets kilometers thick for over 100,000 years, was ending. The Laurentide ice sheet, which covered most of modern-day Canada and stretched down into the northern United States, was retreating northward. The Fennoscandian ice sheet over northern Europe was doing the same. Sea levels were rising as the meltwater flowed into the oceans. Coastlines that had been above water for thousands of years were slowly being swallowed by the sea. And on the land that was being uncovered and warmed, life was returning in abundance. Forests were spreading northward into territory that had been tundra for millennia. Grasslands were expanding across what is now the American Midwest and the Eurasian steppe. And the animals that lived in these environments were staggering in their diversity and scale. North America alone was home to woolly mammoths, mastodons, giant ground sloths that stood as tall as a modern elephant, short-faced bears larger than any bear alive today, saber-toothed cats, American lions, American horses, American camels, dire wolves, and giant armadillos. The megafauna of this warming world were as spectacular and as varied as anything that had ever lived on the continent. The people sharing this world with these animals were not primitive either. The Clovis people, named for the distinctive stone spear points found near Clovis, New Mexico, and now known to have been present across virtually the entire American continent, were sophisticated hunters who had developed remarkable tools and strategies for pursuing and killing the largest animals on Earth. Their spear points are works of precision craft, carefully shaped from specific types of stone that they transported across hundreds of kilometers. They moved through a landscape of unimaginable abundance, following herds of animals that had never learned to fear a human hunter. Across the ocean in what is now the Middle East and Turkey, other communities were doing something even more unprecedented. At Göbekli Tepe in southern Turkey, people were gathering in coordinated groups of hundreds and quarrying, transporting, and erecting massive stone pillars carved with extraordinary skill and precision. This was not a small local effort. It was an organized project spanning multiple generations, requiring the coordination of labor and resources across a large area. And the people doing it were hunter-gatherers, nomadic people with no agriculture, no permanent villages, no metals, no writing, just the accumulated knowledge of tens of thousands of years of human observation and ingenuity. In the Levant, communities were beginning to harvest wild grains in a systematic way, not yet farming, not deliberately planting and cultivating, but managing wild stands of wheat and barley with enough organization that the distinction between foraging and farming was beginning to blur. The people doing this had learned, over generations, exactly when and where the grain ripened, how to store it, how to process it. They were standing at the threshold of an agricultural revolution that would transform the entire human species. The world in 13,000 BC was a world of possibility, of abundance, of people who had survived impossible conditions for 100,000 years and were finally, tentatively, beginning to build something more permanent than a camp. And then the sky changed. The Greenland record, a switch being flipped. The most precise record of what the Younger Dryas did to the Earth's climate comes from ice cores. Deep in the Greenland ice sheet, scientists have drilled cylinders of ice that descend through hundreds of thousands of years of accumulated snowfall. Each layer represents a year. Each layer contains trapped air bubbles, dust particles, chemical traces, and biological material that together paint a detailed picture of what the atmosphere was like when that snow fell. Reading an ice core is like reading a history book written in chemistry, and the chapter on the Younger Dryas is one of the most dramatic passages in that book. In the GISP2 and GRIP ice cores drilled from central Greenland, two of the most extensively analyzed paleoclimate records ever produced, the start of the Younger Dryas appears not as a gradual change, but as a sharp boundary. Within the span of a few decades, possibly within a single decade, the chemical composition of the trapped air shifts dramatically. Temperatures in Greenland, reconstructed from oxygen isotope ratios, dropped by 10 to 15 degrees Celsius. Dust levels in the atmosphere spiked. The air over Greenland became thick with particles carried from exposed, dried-out landscapes by howling winds. Methane levels dropped as the world's wetlands froze. And then, for 1,200 years, the record holds at this new, colder baseline. 1,200 years of near-glacial conditions, in a world that had been warming for millennia. The ice core record also contains something that researchers have been arguing about since it was first identified. At the exact boundary layer, the year the Younger Dryas began, there is a spike in certain chemical signatures: platinum, ammonium, nitrates. The platinum anomaly is particularly striking because platinum is rare in the Earth's crust, but common in extraterrestrial objects, asteroids and comets. A spike in platinum at a specific layer in an ice core is one of the markers scientists use to identify major impact events in the geological record. The platinum spike at the end Cretaceous boundary, the layer corresponding to the asteroid impact that killed the dinosaurs 66 million years ago, is one of the most famous examples in all of geology. The platinum spike in the Younger Dryas boundary layer is smaller, but it is there, and it is synchronous across multiple ice cores and sediment records from different parts of the world. With the moment the cold began, something happened, something that left a chemical fingerprint in the ice, and AI is now helping researchers understand what that fingerprint means. What died and what disappeared. The extinctions that occurred during the Younger Dryas are among the most rapid in the history of the Earth since the end of the dinosaurs. In North America, approximately 35 genera of large mammals went extinct in a geological eye blink: the woolly mammoth, the mastodon, the saber-toothed cat, the American horse and camel, the giant ground sloth. Animals that had survived dozens of previous ice ages and warming periods over millions of years, suddenly gone. At the same moment, the Clovis culture, the people whose distinctive spear points are found from the Atlantic to the Pacific, effectively disappear from the archaeological record. Their tools stop appearing in sediment layers dated to the start of the Younger Dryas. Two collapses, simultaneous. At the exact moment, a dramatic climate shift begins. And that is the central mystery, because these animals were not fragile. The woolly mammoth was literally built for cold. Its coat, its fat, its teeth were all adaptations to exactly the kind of conditions the Younger Dryas brought. And yet they died, all of them, suddenly. Climate change alone does not explain this. Something else had to have happened. The official explanation, and the problem with it. The mainstream scientific explanation for the Younger Dryas is a story about water. As the last ice age glaciers melted, they created an enormous lake of fresh water along the edge of the retreating ice sheet. Lake Agassiz covered most of what is now central Canada, larger than all the modern Great Lakes combined. For thousands of years it was held in place by an ice dam along its northern margin. Around 12,900 years ago, that dam broke. A catastrophic volume of cold freshwater flooded into the North Atlantic in geological terms almost instantaneously. The Atlantic Ocean runs a circulation system, a conveyor belt of warm, salty water flowing north along the surface, cooling, sinking to the ocean floor, and flowing south again. This is what keeps northwestern Europe warm. London is at the same latitude as Calgary. Without this circulation, it would have a climate to match. The freshwater from Lake Agassiz disrupted everything. Freshwater is lighter than salt water. The surface water could no longer sink. The conveyor belt slowed or stopped. Heat stopped moving northward. The Younger Dryas had begun. This explanation is well supported and widely accepted. Most climate scientists teach it as the answer, but it does not explain the platinum in the ice cores. It does not explain nanodiamonds on 4 continents. It does not explain what killed the megafauna. And it does not explain why the change happened within years, not decades, not centuries, when previous disruptions to the Atlantic circulation had been far more gradual. Something is missing, and AI is finding it in the ground. The layer in the ground that should not be there. Across the world, buried in sediment layers that correspond to the very beginning of the Younger Dryas, there is something that has no business being there. A thin layer, sometimes only a few millimeters thick, found at archaeological and geological sites across North America, Europe, the Middle East, and South America. It is not volcanic ash. It is not the product of any known geological process, and it contains materials that, in the words of the researchers who have spent years analyzing it, can only have come from a cosmic impact event. Nanodiamonds, microscopic diamonds that only form under the extreme pressure of a cosmic impact. Platinum and iridium, rare in the Earth's crust but common in asteroids and comets, the same signature found at the dinosaur-killing boundary 66 million years ago. Magnetic microspherules, metallic droplets formed when rock is instantly vaporized and rapidly cooled, and melt glass fused with shocked quartz, materials created only at temperatures and pressures that volcanic eruptions cannot produce, found at confirmed impact craters and nuclear test sites, and nowhere else on Earth. All of it in the same thin layer, at the same geological moment, on 4 continents. In 2024, researchers at the University of South Carolina, working with colleagues at UC Santa Barbara, published new analysis of this layer at sites across the eastern United States, New Jersey, Maryland, and South Carolina. Using high-resolution microscopy and chemical analysis, they examined the shocked quartz from these sites in detail. What they found was not the standard pattern of parallel lamellae that you see in shocked quartz from a ground impact. It was something different, a web-like intersecting pattern of fractures, irregular and meandering, with surface and subsurface fissures crossing each other at multiple angles. This specific fracture pattern, the researchers argue, is characteristic not of a ground impact, but of an airburst, an explosion in the atmosphere. When an extraterrestrial object explodes above the ground, the pressure wave it generates is different from the pressure wave of a ground strike. It comes from above, at an angle, producing the irregular web-like fracture patterns found in these quartz grains, rather than the clean parallel lamellae of a direct impact. The implications of this finding are significant. It means the event that left this layer did not necessarily leave a crater. A large enough airburst, an object exploding in the atmosphere before reaching the surface, could produce the thermal pulse, the pressure wave, the vaporized material, and the widespread fires needed to explain the Younger Dryas evidence without leaving a single identifiable crater in the ground. Which explains why, after nearly 2 decades of searching, no crater associated with the Younger Dryas impact hypothesis has been found. The size of what hit. If the impact hypothesis is correct, and it is worth being clear that this is still a contested scientific hypothesis, not an established fact, what hit the Earth at the start of the Younger Dryas was not a single object. It was a comet, fragmented, broken apart during its long journey through the inner solar system into pieces, possibly hundreds, possibly thousands of them, of varying sizes. The parent comet before fragmentation is estimated to have been enormous. Some researchers put its original diameter at around 100 kilometers. To put that in perspective, the asteroid that wiped out the non-avian dinosaurs 66 million years ago was approximately 10 to 15 kilometers across. The proposed Younger Dryas impactor was many times larger before it broke apart. What the Earth encountered was not one massive impact but a swarm, a spread of fragments arriving over a period of time, hours, days, possibly longer, with different pieces hitting or exploding above different parts of the Earth. The largest impacts are believed to have occurred over the Laurentide ice sheet, the vast glacier covering what is now Canada. This is, paradoxically, why no crater has been found. Ice does not preserve craters the way rock does. A comet fragment striking a glacier kilometers thick would blast through the ice, vaporize enormous quantities of meltwater, and produce a temporary crater that would be filled and smoothed by the surrounding ice within a geologically short period of time. By the time the ice sheet finished melting, which it did over the following thousands of years, any evidence of what struck it would have flowed into the oceans as meltwater and been lost. But the effects of those impacts would not have been lost. They would have been catastrophic. An airburst large enough to deposit the materials found in the Younger Dryas boundary layer across 4 continents would have released energy equivalent to thousands of nuclear warheads detonating simultaneously. The thermal pulse from such an event would have ignited everything flammable across an enormous area. The charcoal and soot found in sediment layers from the Younger Dryas boundary provide evidence of exactly this kind of widespread burning. A pressure wave from a major airburst would have devastated ecosystems across a continental scale, and the debris thrown into the upper atmosphere by multiple simultaneous impacts and airbursts would have blocked sunlight, cooling the Earth's surface and potentially triggering or accelerating the ocean circulation collapse that mainstream science identifies as the primary cause of the Younger Dryas. In this version of events, the two competing explanations, the ocean circulation theory and the impact hypothesis, are not alternatives, they are sequential. The impact caused the rapid melting of parts of the ice sheet. The meltwater flooded into the North Atlantic. The circulation collapsed. The cooling lasted 1,200 years. One catastrophe, triggering the next, and the next, and the next. What AI is actually finding, and how. The Younger Dryas impact hypothesis was first proposed in 2007 by a team of researchers led by Richard Firestone, Alan West, and James Kennett. Their original paper, published in the Proceedings of the National Academy of Sciences, identified the thin layer of anomalous materials at the Younger Dryas boundary at multiple sites across North America. The response from the scientific community was immediately skeptical, and that skepticism has never entirely disappeared. Some researchers have attempted to replicate the nanodiamond findings and reported different results. Some have argued that the shocked quartz could be explained by other processes. Others have pointed to the absence of any confirmed crater as fatal to the theory. A 2025 review in the Skeptical Inquirer concludes bluntly that the hypothesis has failed, that recognized impact markers were not reliably found, and that the evidence base does not support the conclusion of a major impact event. But the proponents of the hypothesis have not retreated. If anything, the evidence base has grown since 2007. Over scores of peer-reviewed papers, published in dozens of different journals, from researchers at institutions across North America, Europe, the Middle East, and South America. The same thin layer of anomalous materials has been found and analyzed. Independent teams, not affiliated with the original Firestone group, have identified the same platinum anomalies, the same microspherules, the same melt glass, the same shocked quartz at site after site across 4 continents. The 2024 studies from the University of South Carolina and UC Santa Barbara add new sites and new material to the database. Every year, the list of confirmed Younger Dryas boundary sites grows longer, and this is where AI is changing the nature of the debate. The fundamental problem with analyzing the Younger Dryas impact hypothesis by traditional methods is the scale of the dataset. The evidence is distributed across dozens of countries, in sediment layers analyzed by different research teams, using different methods, producing results that are individually suggestive but difficult to synthesize into a coherent global picture by any individual researcher or team. The pattern, if there is one, exists across the entire dataset, and until recently, no tool existed that could process the entire dataset at once. AI can. Researchers are now feeding chemical analysis data from Younger Dryas boundary sites across the globe into analytical systems that can compare the signatures simultaneously, looking for correlations, identifying which markers appear together most consistently, mapping the distribution of impact evidence across the surface of the Earth, and modeling what kind of impact event could produce a distribution that matches what is found. The AI does not have a prior opinion about whether the hypothesis is true or false. It simply finds patterns in data that no human researcher could hold in their head at once. The spatial distribution analysis is particularly significant. If a fragmented comet hit the Earth, the debris from the impact and airburst events would be distributed in a pattern determined by the direction and angle of approach, the size and number of fragments, and the atmospheric and surface conditions at the time of impact. By mapping where the Younger Dryas boundary layer is thickest, where the platinum and nanodiamond concentrations are highest, and where the evidence of burning is most intense, AI can begin to reconstruct the geometry of the event, to work backwards from the debris field to the source. The results of this analysis are still being refined, but they are consistent with a major airburst or swarm of airbursts over the Laurentide ice sheet in North America, with secondary effects spreading across the northern hemisphere and, at lower intensity, into the southern hemisphere as well. The distribution of the evidence, as AI is mapping it, is not random. It has a shape, and that shape is consistent with something arriving from a specific direction, hitting a specific target, and spreading its effects outward from that point. This is not proof, the debate is not settled, but it is the most sophisticated analysis of the Younger Dryas evidence ever conducted, and it is not making the impact hypothesis look weaker. The Torrid meteor stream, where the comet came from. Every year, in late October and early November, the Earth passes through a stream of debris left by a fragmenting comet. The result is the Torrid meteor shower, one of the longest-lasting annual meteor showers, with slow-moving fireballs appearing to radiate from the direction of the constellation Taurus over a period of several weeks. The torrid stream is unusual among meteor showers in several ways. It contains an unusually high proportion of large fragments, objects big enough to survive entry through the atmosphere and potentially cause significant damage on the ground. It is associated not with a single parent comet, but with a complex of related objects, multiple comets and asteroids that appear to be fragments of a much larger body that broke apart in the relatively recent past. Astronomer Victor Klube and his colleague Bill Napier proposed in the 1980s that the torrid complex represents the remnants of a massive comet. They called it Proto-Encke, that entered the inner solar system thousands of years ago and has been gradually fragmenting and dispersing ever since. The specific timing and geometry of the Earth's encounters with this debris stream have varied over millennia as the orbits of both the Earth and the debris have evolved. 12,800 years ago, the Earth's orbit through the torrid stream looked different from what it does today. And some researchers, using orbital mechanics calculations and AI-assisted modeling of the debris stream's evolution over time, have proposed that at that specific moment, the Earth passed through a significantly denser region of the stream than we encounter today, a region containing fragments large enough and concentrated enough to produce the kind of catastrophic event the Younger Dryas boundary layer appears to record. If this model is correct, the Younger Dryas impact was not a random event, a once-in-a-billion-years collision with an asteroid that happened to be in the wrong place. It was a predictable, periodic consequence of the Earth's relationship with a known debris stream, a stream that still exists, a stream that the Earth still passes through every year, a stream that still contains large fragments whose precise orbits have not all been mapped. The implications of this are not comfortable to sit with for very long. The survivors and what they built. Whatever the cause, ocean circulation collapse, cosmic impact, or both in sequence, the people who lived through the Younger Dryas faced conditions that are genuinely difficult for any modern human being to fully imagine. The world they had known, a world of abundance, of retreating glaciers, of spreading forests, of enormous herds of megafauna across a vast and warming continent, was gone, replaced within the span of a human lifetime by cold and wind and ice and the disappearance of the large animals that had been the foundation of their diet, their culture, their entire way of life. The archaeological record of the Younger Dryas is, in large parts of North America especially, an almost empty record. The dense layers of Clovis artifacts found in sediments from before the event thin dramatically in the layers that follow it. The evidence of human habitation across large regions of the continent becomes sparse, scattered, hard to find. This does not mean people were gone. It means they had retreated to warmer refuges, to coastlines where marine resources were still available, to smaller territories that could support smaller groups. They survived. Our existence is proof of that. But they survived in a drastically reduced and changed form. The rich, abundant world of the Clovis culture, with its enormous prey animals and its apparently continent-wide cultural unity, did not survive. What came after was smaller, harder, more fragmented. And then, 1,200 years later, the Younger Dryas ended. As suddenly as it had begun, within decades, in the Greenland ice cores within perhaps a single decade, the cold released its grip. Temperatures rose. The glaciers retreated again, this time permanently. The world began warming again toward the climate we know today. And the people who had survived the Younger Dryas, or whose ancestors had survived it, came out of their refuges into a changed world. A world that had lost its megafauna, a world that was warmer and wetter, and in many ways more hospitable than the one that existed before the catastrophe. A world that still had abundant plant foods, fruits, seeds, grains, tubers, even without the large animals that had previously been the primary food source. And something remarkable happened. Within a few thousand years of the end of the Younger Dryas, agriculture appeared, independently, in at least 8 separate locations around the world. In the Fertile Crescent of the Middle East, wheat and barley were domesticated. In China, rice and millet. In New Guinea, taro and bananas. In Mexico, maize, beans, and squash. In the Andes, potatoes and quinoa. In West Africa, sorghum and pearl millet. In Eastern North America, sunflowers and squash. All of these, developing independently, within a few thousand years of each other, in the aftermath of the Younger Dryas. The timing is striking enough that some researchers have begun to wonder whether the relationship is causal, whether the Younger Dryas, by eliminating the megafauna that people had depended on for hunting, by forcing communities into smaller territories with more intensive use of plant resources, by creating the demographic pressure and resource scarcity that drives innovation, was not just something humanity survived, but something that, in surviving, changed them. That pushed them toward agriculture not as a choice, but as a necessity. That the catastrophe which nearly ended the human story was also, in some deep and terrible way, what accelerated its next chapter. This is speculative. Causation is extraordinarily difficult to establish across 12,000 years of human history, but the pattern is there. The Younger Dryas ends, and the Neolithic Revolution begins. Göbekli Tepe, memory carved in stone. There is one more thread in this story, and it connects the Younger Dryas to everything else in this series. Göbekli Tepe was built immediately after the Younger Dryas ended. The oldest layers of construction date to approximately 9,500 BC, within a few centuries of the end of the Cold Period. The people who built it were among the first generations to live in a world that was warming again, that was becoming abundant again, that was becoming something other than the long, cold nightmare of the Younger Dryas. And if Martin Sweatman's AI-assisted analysis of Pillar 43, the Vulture Stone, is correct, if those carvings really do record the positions of the constellations at the moment of a catastrophic impact event around 10,950 BC, then Göbekli Tepe is not just a temple, it is a memorial, built by people who had survived or whose parents had survived or whose grandparents had told them about surviving. The worst thing that had ever happened to the world. They carved it in stone, 12,000 years before we developed the tools to read what they had written. Think about what that means. These people had no writing. They had no way to record a historical event in words that could be read by future generations. But they understood, in a way that the experience of living through or hearing stories of a civilization-ending catastrophe would make very clear, that stone lasts. That if you carve something carefully enough into a large enough stone, it will still be there long after every person who remembers the original event is gone. Long after every oral tradition has been corrupted by time. Long after the living memory of what happened has faded into myth. So they carved the sky. They recorded the exact positions of the constellations at the moment the catastrophe struck, and they buried the whole thing under meters of soil to protect it. A time capsule sealed at the end of the Stone Age, designed to be found and read by people who would one day have the tools to understand what it said. We are, it appears, those people, and AI is the tool. Whether or not Sweatman's specific interpretation of the Vulture Stone is correct, and it remains contested among archaeologists, the impulse behind Göbekli Tepe is undeniable. These people felt compelled to record something, to preserve knowledge across what they understood would be a vast span of time, to speak to the future. The fact that they built the world's first temple not to celebrate prosperity, but in the immediate aftermath of a catastrophe, is worth sitting with. They did not build Göbekli Tepe because life was good and they wanted to give thanks. They built it because something terrible had happened, and they wanted to make sure it was never forgotten. The debate that is still happening. It would be dishonest to present the Younger Dryas impact hypothesis as settled science. It is not. The debate is genuine, the stakes are high, and serious researchers disagree, not on the periphery, but at the center of the question. The critics make real points. No crater has been found. Some attempts to replicate the nanodiamond findings have failed. The spatial distribution of the impact markers does not match what some impact scientists would expect from a major airburst over the ice sheet. A 2025 review in the Skeptical Inquirer, written by respected researchers in the field, concludes that the hypothesis should be abandoned as a failed theory whose evidence base has not withstood scrutiny. The proponents make equally real points. The evidence base has grown steadily since 2007, not shrunk. Independent teams on multiple continents have replicated the core findings. The spatial distribution of markers across 4 continents is not easily explained by any known terrestrial process. The synchronicity of the platinum spike, the nanodiamond layer, the melt glass, and the charcoal layer with the onset of the Younger Dryas is striking in a way that demands explanation. The absence of a crater is explained, plausibly if not definitively, by the ice sheet hypothesis. Impacts over glaciers do not leave permanent craters. What AI is doing in this debate is forcing it onto a larger playing field. Instead of individual sites analyzed by individual teams producing results that can be disputed or confirmed one at a time, AI is now processing the entire global dataset simultaneously. The patterns it finds, or does not find, will be harder to dispute than any individual site analysis. The spatial modeling it produces will either support or contradict the geometry of a major impact event. and the ice core analysis it is conducting across multiple records simultaneously is looking for atmospheric signatures that would be difficult to explain away if found. The answer is not in yet, but the question is being asked at a scale and with a precision that was not possible before AI entered the field. And that matters, because the Younger Dryas impact hypothesis is not just an academic dispute about what happened 12,000 years ago. It is a question about whether the Earth is periodically struck by debris from a fragmenting comet, whose remnants are still crossing our orbit every year. A question about whether what happened 12,900 years ago could happen again, and if so, whether we would see it coming. Could it happen again? The Taurid meteor stream still exists. The Earth still passes through it every year. The large fragments whose existence has been proposed within the stream, objects potentially hundreds of meters across, large enough to cause regional or continental devastation, have not all been identified and tracked. Their orbits have not all been calculated. Their positions 12 years from now, or 50 years from now, or 500 years from now, are not all known. This is not a comfortable place to end up, but it is where the evidence leads. The good news is that we are no longer in the position of the people who stood under the changing sky 12,900 years ago with no warning and no understanding of what was happening. We have space telescopes, we have radar arrays, we have AI systems processing astronomical survey data around the clock, identifying near-Earth objects, calculating their orbits, assessing their potential for impact over timescales of decades and centuries. The Catalina Sky Survey, the Pan-STARRS project, the future Rubin Observatory. These are systems designed specifically to find the objects that could hurt us before they do. And AI is making those systems dramatically more effective. The same analytical power that is finding impact markers in 12,000-year-old sediment layers is also scanning the sky for what might come next. Processing more data, faster, with more precision than any purely human effort could achieve. The Younger Dryas is not just ancient history, it is a data point, a record of what the Earth has endured, what it has survived, what it has lost, and what human beings, in the aftermath of losing almost everything, managed to build. We went from the edge of extinction to agriculture and civilization within a few thousand years, not despite the catastrophe, possibly because of it. AI is helping us read that record more clearly than we ever have. And if the sky changes again, if the debris stream delivers something larger than the shooting stars of the annual Taurid shower, we will not be standing in the dark watching the world change around us with no idea why. We will know, and this time, we will be looking up. 12,800 years ago, something hit, or something broke, and the world almost ended. The animals died, the cultures vanished, the cold came back and stayed for 1,200 years, and the people who survived rebuilt everything from nothing in a changed world. The debate about exactly what caused it is still happening, but the evidence AI is finding in the ground, on 4 continents, at the same geological moment, is making the impact hypothesis harder to dismiss with every new study. What do you think happened? Ocean? Comet? Both? Drop your answer in the comments. This is exactly the kind of question I want to hear your theory on. Next week, the Great Pyramid. AI thermal imaging has found hidden chambers inside it that no living person has ever entered. Subscribe so you do not miss it. See you then.